Hello. Like we filled the perfect 4 minutes with small talk, so I hope everybody wanted to joined. Okay, so I prepared exercises 96, 97, and 101. And yeah, they're very formal. So this chapter, as you mentioned, is very formal, but when you kind of see the examples, you see that it's not as complicated as, the chapter makes it to be, I think, or, to understand the intuition, it's very easy, but if you audit things later, you really need to understand it thoroughly. Okay, so the idea is, really need to separate the idea of, what do you want to prove in a SNARK? How do you put it in mathematical language? How do I actually make it a problem, a statement, and things like that? So exercise 96 is actually just a beginner's exercise. So the question in the exercise is, we are supposed to be defining a decision function over a language, which consists of all solutions to the equation 5x plus 4 equals 28 plus 2x, and over f13. And then we also need to provide a constructed proof for the claim, for the statement, there exists a word in this language. And then we should verify the proof. Okay, so what does all of this mean? So in this chapter, what we're going to do is we're going to have a sigma, which is going to be any set, and the sigma star is the set of all the strings of finite length from the elements from this alphabet, including the empty string, so also a word which doesn't consist of any things. So this is the language, and this language is called the alphabet. There's a language, and this set is called the alphabet of the language, and the elements are called letters. And if we build elements from language, these are called words. And then the language, of course, has some kind of grammar, and we say that two languages are equivalent if they have the same set of words. So the thing is, for SNARKs, we need to understand, as I mentioned, is something the proof that I want to give you, is the proof correct or is it incorrect? I cannot just give you a mathematical problem and say, give me solutions for it. And if there's no solutions, it's a different kind of a SNARK has a different kind of is in a different environment, because actually what we're doing is we're doing interactive oracle proofs. So we have to understand the decision problem, and we have to understand that we're supposed to be having a deciding relation, meaning is something a word in a language or not? So this is how it's formally defined. So we're going to define the grammar as a decision function, where we say that all the words that are in the language, they are true to this deciding function, deciding relation. So this is the idea of it. And in general, you can think of the statement that we're later we're always going to say, build a SNARK for the statement. And the SNARK definition, zk-SNARK says that we're going to prove that the statement is true. The prover says that the statement is true. So what is the statement? The statement is some kind of claim that some language contains a word. So there exists some X and L. And this is what we're going to try to do. And then the proof is constructing a proof for this, and the proof can be verified by checking that the relation is actually true. Okay, so this is the idea, and I just wrote down this example because I thought it's easier. So if you just think of all the bit strings, you would have the alphabet would be 0, 1, would be the letters. Words would be something like 1, 0, 1, 0, 1. And now we're defining a language where the grammar is supposed to be something like the zeros and ones should be alternating. So this word is going to be in the language, and this word where we see here 1, 1, 1, it's not alternating, is not in the language, right? Okay, and if we want to formalize this, how to formalize this weird alternating zeros and ones, we are going to build this grammar, this decision function here, which is going to go from the alphabet consisting of the letters 0 and 1 with the 0 word to true or false. this is the relation, and what we're going to take in is a finite string where we will have x1s to xn's of 0, 1, and the deciding relation will say true if x y minus 0 is not the same as x y for all the y's from 1 to n. Sorry, I wrote it a little bit short, but yeah. And it will say false for everything else. So this would be the formalization of this grammar. And then I can tell you, okay, so I have a proof, like the claim would be something, there exists a word in this language, and then we have to, like, this is the claim, this is the statement, and I want to prove the statement, so I'll give you one word in this language, for example, this one, 10101, and then we can verify this by checking that R of this word is going to be true or false. And if I gave you a wrong word, then it's going to be false, and then I did not make you, the proof is not verified, and I didn't give you a correct proof, right? So for the statement that this language has a word. So this is the idea of the whole chapter, of this like first part of the chapter, formalizing these problems. So going back to the thing that we are supposed to be doing in this exercise, we have the alphabet of F13. And we're going to take strings of x1 to xn, and the deciding relation, so R of the exercise, is going to be that this string is going to be built on, like, it's going to be pointing to true if n is 1, so we're only having one variable here, right? And if this equation holds, so f x1 plus 4 equals 28 plus 2 times x1. And all the other parts is going to be false. Okay, so now I want to, like, the other part of the exercise was saying, so we wrote a decision function for this language, and now there's a statement, a claim, there exists a word in this language, and we have to give a proof. So to say there's a word in a language, we need to find a solution to this equation, such that we can say there is something that solves this equation, there exists a word in this equation, some x, something in this, like, just going to be like a string of these elements of F13. In our case, it's just n times 1, so there's only one element of F13. So let's solve the equation to provide a proof. So we have here the equation. So I put in F13, we can still like do the inverse addition, right? So we're going to put all the things of an x and to put it on one side. I'm going to add here the that is 4, and like we're going to, like, we have this, and then in modulo 13 we have in the end 3x equals 11, and now we have to find the inverse of number 3, F13, and we have to multiply 3 by something, which will be 1 more 13, so that's 9. So we found a solution. So we need to multiply here 11 by this inverse of 3, which would be 9. So this would be x. So 11 times 9 is 8 mod 13, and that's going to be the x, the solution to the equation. So 8 is a constructive proof, and we can now check the relation for the string containing the 8. So meaning inserting 8 here and seeing, oh yeah, 8 will actually hold this equation, meaning the relation is going to give out true, and that verifies our proof. So I hope this helps to understand this, like, a little bit complex or very detailed definition. But that will help us later to actually make claims and prove them in a SNARK. So I picked another, so this is exercise 97, where we have a similar thing. Here we are given already the decision function. We are now in the modulo 6 arithmetic, zx. And we have this decision function where we again have n equals 1, so only one element in the string, and the x1 should fulfill the equation of 3x1 plus 3 equals 0. So the exercise says that we should compute all the words in this language and provide a constructive proof for the statement that there exists a word in this language and verify the proof. So let's first look at what words exist in this language. So we're in set Z6 with n equals 1. So we only have 0, 1, 2, 3, 4, 5. In the language, there's also the 0 element here. Sorry, there's also the empty string in there, actually. And okay, so to provide a constructed proof, we have to find some x which will hold this equation, where this equation holds for in modulo 6 arithmetic. So I've written them all down, and you can verify by yourself. So we could, for example, for 1, we have 3 times 1 plus 3. That's 0 modulo 6. So that holds this equation. So we have a constructive proof for the statement. This would be the constructive proof. And we can check the relation, and the relation will evaluate to true. So that verifies the proof. Okay, so I'm repeating a lot of times these words just to get very used to the relation and the statement and like evaluating to true. Okay, so and the last exercise that I prepared is we're here like talking a little bit more about proofs actually, because we've talked about proofs before, but here we are now in the circuit setting. So I'm not sure if you're already through the whole chapter, but this was the first exercises that I presented. They were about just constructing the problem, constructing the language, constructing the deciding relation. And then from there, we're looking at how we should actually build an R1CS and how we should build a circuit, and then how we are building a QAP, a quadratic arithmetic program. So this exercise here is now considering that we already have a circuit for the curve equation for a tiny dot-dot curve. And we are supposed to construct a proof now that something is on this curve. And then we have to verify this proof. So this is the idea of this exercise. So this is what the exercise wants us to do. We have to consider the circuit, and we have to construct a proof for this instance. Thought it's a good thing to like look at it again. So this is the example that the exercise is referencing. So let's look at it. So we are going to look at the tiny dot-dot curve and over F13. So a pair of field elements of x and y over F13. That pair is a curve point if this equation holds, right? So we have like now the idea is that we want to transform this into an algebraic circuit, and we then have to construct a proof in this algebraic circuit setting, right? So let's like think about it again through this example from the book. So we are reconstructing it a bit, and we are shifting things such that we can actually write it as an algebraic circuit. So we are just putting things on the other side, and we're getting this expression on the right. So in this expression on the right, we can actually write it as a circuit. So always when we get x and y's, which verify this equation, where this equation, this expression on the right is 0, these points of x and y are going to be on the curve, right? So this is the idea. And now we can, through those multiplications and additions, we can actually write those as gates, and we can get a circuit. A circuit will look something like this. Okay, let me just show you a bit. So there, like I just highlighted like some things. For example, oh, sorry, was there a question? Or okay, maybe I'll finish that, and if you have questions in the chat or pin me. So I just highlighted some points. So for example, we have the quadratic expressions here, right? X times x, y times y. So, and we see that actually in the algebraic circuit. So there's a multiplication node here, and the multiplication node has 2 incoming edges, and both incoming edges come from the same input variable x. So this is where the quadratic x multiplication is coming from, and the same for y. So for example, this is where these like come in here. And you can like, if you want to build it yourself, it's actually not that hard. I would always go from inner to outer brackets that you have built. So for example, if I look at this part, we have here an inner bracket of the quadratic expression of y. So it would be an outgoing edge from this multiplication node. And then we have to multiply it by 12. So we have to draw an edge here from this node to another multiplication node where another incoming edge is the 12. And then it's going to be an outgoing edge. And we can do similar things here. For example, I just highlighted this because I thought very interesting, like it's the most interesting part because it's incoming edges. So what we're doing here, we're having two multiplication nodes where we multiply x by x and y times y with y. So here and here. And these are again multiplied. So this is the mole here. So we have outgoing edges from these that are going in again into another multiplication node. And this result is then going to be multiplied again with an 8. So this is where this multiplication node comes in. So this is how the circuit is going to be built. And I just wanted to mention, I just picked like the example 125 because it was mentioned in the exercise. Depending on how you bracket this, like how you bracket this thing, you might have a different circuit because it really depends, and this is not a unique representation. Okay. Yeah, so what incoming edges do we have? We have here the incoming edge here from the x and from the y's. And the last outgoing edge, actually, we need to constrain it to 0 because we want the point to be on the curve, right? So in the book, Mirko wrote it as a function to make it a little bit more intuitive, but this is actually supposed to be constrained to 0. Okay, so now we want to actually write a proof for this. So let's go back. So we have the circuit from example 125 for the language. And now we have an instance 11.6, meaning the public values are 11.6. And we have to construct a proof. So is the x value, is x equals 11 and y equals 6, is that a point on the curve? And if so, give us a proof. This is the idea of this exercise. So we're going to do that by actually, as a prover, we need to be executing the circuit, and we need to find the intermediate witness values. And since we execute the circuit, we'll find those intermediate witness values, and then we can give a whole proof. So what we're going to do is we're going to input 11 and 6 here, and we're going to execute a circuit. Like I already did that for you because I'm presenting the exercise, but if you want to try it out yourself, you can totally do that. So 11 times 11 in modulo 13 arithmetic is going to be 4. And 6 times 6 in modulo 13 arithmetic is 10. So the outgoing edges here will be 10. And this is the first. This S3 here, which when we did not know what was a witness and what was an instance, we labeled all of the edges by S's. But since now we're going to look at instances and at witness values, we're going to be able to actually label them according. So this will be the first intermediate witness value being 4, and the second one will be 10. And then from those two, we can actually get the third intermediate witness value. So by multiplying 4 times 10, which is going to be 1 in modulo 13 arithmetic. And then we need to execute the whole circuit just to make sure that actually everything is constrained and actually the proof is correct for us as a prover. So as a prover, I get the input values, which are instances in this case, and I execute a circuit and I find intermediate witness variables 4, 10, 1. So my proof in the end would be 11, 6, 4, 10, 1. If you're wondering at this point where the zk comes in, this has nothing to do with zk because here we're just in an algebraic circuit, we're just generating a proof which is not zk, it's just a proof for something. So this is why we can actually just give the verified as whole proof. And through the zk protocols that we will learn later, you will see that this witness values, the verifier will not get these values directly. He will not see like at 11, 6, 4, 10, 1. He will see another representation, so he will not know the witness variables. I hope this helps. I got these questions before, so I hope this helps. So in this specific setting, our proof for this statement that something is in this language is for the instances 11 and 6. The proof is 11, 6, 4, 10, 1 for the circuit. So this circuit is representing the grammar, and this is the proof for it. And the verifier can then execute the circuit again with all these assignments and decide whether the circuit, whether its proof is correct or not, if this is like a valid assignment or if this is not a valid assignment. So I hope this helped to get a little bit of intuition for this chapter. And that was it from me, actually. It was very short. Yeah.
Hi, just a quick question regarding that same example. So when we're talking about the constructive proof, that includes not only the instances, but also the witness? Or is it just the witness?
Yeah, no, it's both. Wait, I can share again. Yes, it's both, actually. And just share again. Because... yes, it's the instance and the witness values, because the proof consists of, I don't have it here right now because I don't have the book open.
But also just focusing on this.
So the proof is always the instance and the witness values, because they together, these together are actually part of that axe that I showed before, so of the word, which is then separating the word into an instance part and a witness part.
Gotcha. All right, thank you.
Does it help?
And just one more concern regarding it's labeling these graphs. So like, I think in the next chapter particularly, like you have to draw a lot of these, and I was having a little bit of difficulty regarding that. So for addition nodes, you do not add label. Is that correct?
No, that's not correct. So it depends on what you're doing. So that's why you add the nodes. Wait, I'll maybe show you this. Let's go in here so that more easy. And where was I?
Because there were a set of rules defined, but I'm not sure like how concrete those were, or like how strictly they were being followed, because I saw different examples within the book. Yeah, this one.
Yeah, no, I agree. I see what you mean. So the thing is that we always have, like, it depends on if we're talking about a variable or a constant. And so this is where like this is coming in. So in this specific setting, like if we have kind of annotated edge, we're going to use another annotated edge since it's like incoming from there. Yeah, I don't know if this helps, but we are going to see more examples, so maybe that will help later. But yeah. Okay, sorry, I was like thinking maybe I'll like see a good sentence explaining it, but I think once you get like the idea, it's kind of like a little bit more sense. So kind of like the idea is in general that if you have sync nodes, they have a label, and if you have nodes, like if there's a variable involved, the outgoing node is going to have a label. And if you have a multiplication with an edge where there is a label, you're going to have another label. So that's kind of the idea. I don't know if this helps.
Right, but is this strictly defined just for multiplication? Labels which are multiplications, or does that also include addition?
So it just in this setting just includes the multiplication nodes, because they will change, like it's a change of the value in the setting, but
Okay.
Yeah, I think it's just a little bit more intuitive once you've done a little bit more of those exercises.
Gotcha.
Yeah.
Okay, yeah, I'll just practice a few more then. Thank you.
Yeah, sure. It's a little bit intricate, so it's a little like, yeah, it's a little bit.
Yeah, I have to keep referring back to this page. It's frustrating because, I mean, it doesn't really sink in if you just look at it once.
Totally. And also, I think the thing is also honestly like that. So we're defining it like this in the book, but in a lot of like other applications, a lot of other, like if you look at other examples, people are drawing their circuits in a totally different way. And for example, there are like some people are doing the upside down way where the sink values are the incoming edges, actually. The input's actually not the way around. So yeah, everybody agrees that it's like directed acyclic multigraph, but yeah, it's a little, yeah, people normally don't draw those things at all because, yeah, once you understood the concept, it's like good enough.
Okay.
But
Does that make your job a lot harder because you see different versions throughout the audit programs?
Yes, we do. Yeah, that's it's actually like very annoying because as you will see, like in the next chapter, like you have to understand what needs to be constrained for some things, and to do so, you need to actually like think about it as a circuit sometimes because you need to understand how values are constrained and if that circuit is like actually like constraining them or not. So you need like a good intuition for it, but you also like in the end, you're just looking at code and you kind of like need to understand the compiler exactly, which we're using. So yeah, and then the compiler is doing like specific things. Yeah, so I don't know if this helps. Okay, so yeah, I hope this helps.
It does, thank you.
Sure, nice. And then I see there's a question in the chat by KK Star. So you're asking what's K again and why does it not matter here? Which K? Was it in the exercise that I mentioned, or? I mentioned in the exercise K. Okay, wait, let me share my screen again and we can look at it together because okay, so this was the first exercise that I was describing. I don't really remember mentioning a lot about K. Okay, so I don't see not really a K here. Like in this. Okay, it was the last exercise. Okay, no worries. Okay, wait. Now I'm just curious what the K is. Okay, so this was the last exercise. And I don't think there's a K value. So we only have like a curve equation, which we then rewrite. So there's only X and Y variables here. And then we have I and W edges for the instance and witness values. And so I hope this answers the question. So
yeah, we don't have K here. We only have that in Uniswap.
in uni what?
Uniswap.
Ah.
V2.
Okay, cool. Okay, then I'm happy that
It was a
have
joke.
figured it out. Oh, okay.
And
I was like, wait, very confused.
Yeah, I got a question for
Sure.
the terminology.
Mm-hmm.
So in this page of your notes, I call 11.6, I call it public input. I call
Yes.
14.1 private input, and I call the entire thing business. So we use different terminologies.
Mm-hmm. Yeah, we do. So you're not the only one. So I think, so in our case, we call instance the public input and witness the private input, and we call the whole thing a proof for a statement. And I think there's benefits to both. I think we've also, like, when I started looking at these, like, I've seen things where it was similar to your notation, where people would say the prover has a witness, but then it turns out that everything in the witness is actually public. So it's not a real witness, right? Because then, like, I mean, it depends on how you see it. Like, it's just everything is public, so there's no private input at all. So there is no, like, anybody could take it and get a proof. So that's why we kind of.
Yeah, I learned that terminology probably from CIRCOM, because in CIRCOM, input.json is user input, which is your secret, your private inputs. And if you compile your circuit using SNARK.js, you got a witness. The witness contains everything.
Yeah, I think that's I think that's like the thing. Like, now we're getting, like, I think a little bit more into the SNARK world, and a lot of, like, the notation and the, like, how people talk about things it's not standardized at this point. Like, people will understand a little bit once you talk about it. People will be like, oh, yes, you mean this, you mean that, but it's not necessarily like everybody knows. It's like standardized. It's not like in the algebra and elliptic curves chapter when we talked about a group, or when we talked about some mathematical concepts, everybody was agreeing on it, that this is very, like, new topics, and it's not yet neither standardized nor actually understood. Like, it's not yet, like, there is some books, but it's not taught in this formal way. So I think people have not yet decided on things. So throughout the book, don't be confused. Like, it's good that you mention it, Young. This is how we mention it here in the book, and it's good to know.
Okay, gotcha.
Yeah, just to follow up for the same example. So in my notes for witness 3, I had it labeled as the edge, which is equal to 8. So 8 times 1 is equal to 8. I'm not sure if that's the same or not. At least in the book, W3 was labeled as that one.
I don't. Okay, so in this case, like, why it's not labeled, why this output here, well, wait, here, I hope you see it.
This one.
Exactly, it's not it's not labeled, is because it's kind of like, it's the same as this one, where you're multiplying a labeled edge with a constant. So, and I think maybe you're confusing. Okay, wait. Maybe you're confusing this circuit with another circuit in the book on the same problem, because the thing is, like, it depends just how you bracket things. So if you bracket the thing,
Right. Yeah. No, I think I was looking at the one in the book, which is a little different from this.
Yeah. So there is, if you bracket it this way, you get you would label it.
Okay, I see.
But if you label it in a different way, where you kind of like label 8 times x first, and then you take that bracket and multiply it by the y, the result of 8 times x, for example, you multiply that with y, then the note is different, right? You would first do 8 times x and get an output here, and that would be labeled, and then you multiply that with the S4 in this case here, I think.
So is W3 equivalent to 8 times x squared times y squared, or at least in this case? Or it's just...
W3 is equivalent to...
x squared times y squared.
X squared times y squared. Yes.
Okay.
So in this setting, okay, wait, I'll go down. Exactly. In how I draw the circuit, or exactly, it's equivalent to the output of x squared, which in my setting is W1, multiplied with the output of y squared, which is W2. Okay. So gotcha. W3 is that output.
All right. Thank you.
Sure. Yeah, but these circuits, like if you draw them, as I mentioned, they're never unique. So it's like you can draw it in a lot of different ways. You should still have the same number of constraints in the end, but yeah, it's interesting for sure. Okay, so that was what I prepared for the session. I hope it helps, and I hope it was interesting. And I give the floor to Chin Young.